Swayam Prabha. Digital India. Educated India.
Okay, let's start. So, myself Nidhi Rathi, and I'm a PG scholar at Indian Institute of Science, working with Professor Siddharth Burman. And today, as we've been talking about cake cutting and fair division of divisible resources, we've seen a bunch of algorithms, bunch of existential results which have been told but not yet proved. So, in this particular lecture, the aim would be to prove existence of envy-free cake cut, which is a connected division. So, existence of envy-free cake cut or cake division. Okay. And also note that, so we will be now again coming back to the case where I want contiguous pieces or a connected division. Okay, yeah. So, let me draw that particular diagram which was again made. So, let's say there's a bunch, this big circle represents the set of all allocations. There's a set of allocations which represents the division which provide or which guarantees proportionality, and then there's a set which sits inside which guarantees envy-freeness. So as we have seen that envy-freeness implies proportionality, I know that this is a subset of proportionality. So what I will in this particular lecture prove that this particular set is non-empty. So in particular, I'll show that there does exist an envy-free cake cut, which is a continuous cake cut, and just to represent, it will be something like this is an interval going to agent, let's say A, and second will go to agent B, and so on. So it's not like I'm getting a piece somewhere here, somewhere there, or crumbs of it, but every agent is getting a connected interval such that what is happening, we are ensuring envy-freeness. So just to recall that, so can anyone recall the definition of envy-freeness? What is the equation I should write here? Anyone? So I should write V of A, VAIA is at least V of A, IB for all B and for all A. So no agent should envy any other piece, and in a way he is not envious of any other agent. He is not thinking, okay, I could have gotten that piece and would have been happier. This is not the case. The system has no envy, and therefore it's called envy-free cake cut. It is stable in that particular sense, if you may. Okay, so how do we prove such an existential result? For proportionality, if you recall, we proved it via giving an algorithm, which is the moving knife algorithm, if you all recall. And the algorithm's correctness only told you that, okay, it's a proportional allocation. So now I want to show that there does exist an envy-free allocation, but since we've already seen that computing such an allocation is, let's say, hard, it's computationally hard, it's computationally intractable, and we have seen bunch of not in the case, okay. So remember the result of Stromquist, which was shown, which was said and not proven, but it says that there does not, or this is a symbol for there does not, but okay, there does not exist a finite protocol to compute or to find an envy-free cake cut. Envy-free cake cut, and all throughout I'll be assuming contiguity. So assume they're all connected and or contiguous. Okay. So I will be proving existence, but before that, I'll be proving a really cool combinatorial lemma, which is known as Sperner's lemma. And on the face of it, it does not have anything to do with cake cut. But in and itself, this particular combinatorial result is very fascinating, at least to me. And we'll see how it connects the area of fair division. So I'll be in particular talking about, the first half I'll talk about Sperner's lemma. I'll tell you what it is, and then we'll see how it implies NV-free cake cut, exact NV-free cake cut. Yeah, no approximation here. Okay, so Sperner's lemma doesn't involve any cake cutting or anything, but it does involve triangles. Okay, so what is the setting? Sperner's lemma. It has bunch of other equivalence notions as well, and I will circle back, let's say if I have time at the end or in the coming days. But what it has is, we talk about a triangle, and I'll be drawing this triangle a bunch of times. So, oh, okay, yeah. Yeah, let's say I have a triangle, and I'll denote it by, let's say, T. And along with this triangle, I am given a triangulation as well, something like that. Let's say a triangulation is given, which this means that it's subdivided into smaller or elementary triangles. Let's say something like this. I'll formally state the lemma, but just for the sake of presentation and understanding, I'll work with this very nice looking division or triangulation. So, yeah. So what am I given? I'm given a triangle T, which is a big triangle, which has 3 vertices, 1, 2, and 3. And furthermore, I've given a triangulation of this particular triangle, which just means that this subdivide it into elementary or baby triangles. I'll be calling it elementary triangles from now on. Okay, so this is given to me. So first element of Sperner's lemma is a triangle T. Yeah, triangle T along with the triangulation. And there is a second element also to the Sperner's lemma, which basically is a labeling, and also called as Sperner labeling. How does it work? So currently, the very first property is all these main vertices, these 3 main vertices must get distinct labels. So all main vertices of the big triangle T I started with must have distinct labels. This is my first condition for it to be a Sperner labeling. So let's say this has, okay, I should follow, yeah, okay. So let's say this is given label 1, this is given label 2, and this is given label 3. So the first condition is all main vertices, which are 3 right now, must be given distinct labels. And what is the second condition? Second condition is regarding to the vertices on the boundaries. So in particular, these vertices, as in on this boundary and on this boundary, and similarly on the third boundary as well. So what is the condition here? It says that, okay, so when you are on the, let's say 1, 2 edge, all these vertices on the boundary of it must get a label which is either 1 or 2. It must not get a label which is not coming from the edge 1 or 2. So it should get either 1 or 2, or let's say, let's say it gets 1. Okay, I am sorry, I should follow the example because it would be useful. And let's say this is 1, 2, 3 in this way, okay. So it says that on this particular edge 1, 3, it should get this labels 1 or 3. So let's say I do it 1, 1, 3. So in a way, what am I saying is this particular edge must get labels which it inherits from the extreme points, which is 1, this vertex, main vertex 1 labeled, and the main vertex labeled 1, 3. And similarly, it happens for other edges 2, 3 and 1, 2. So can any one of you give me a labeling for these 3 vertices on the boundary? Like anything. So let's say 2, 2, 3. Yeah, this is a valid labeling till now. And on 1, 2, let's say I give it 1, 1, 2. Yeah. So something like this, which adheres to 2 conditions. So I should write the second condition as well. So, okay. Every vertex on the boundary edge 1, 2, boundary edge 1, 2, which is this particular edge, must get a label which is either 1 or 2. Okay, and similarly, every vertex on the boundary edge 1, 3 must get a label which is 1 or 3. And similarly for 2, 3 edge, the label must be 2 or 3. So these are the components of Sperner labeling, and currently also note that I'm confining myself on a case of triangle. It does generalize to higher dimensions, but for the sake of understanding and again for the ease of presentation, I'll stick to the case of triangle. Yeah. Okay, so the ingredients of Sperner's lemma, are they clear? First, I have a triangle, a big triangle, which is also triangulated among small baby or elementary triangles. And the second is Sperner labeling. You must have a Sperner labeling which says that, okay, the main vertices must get distinct labels and the boundary vertices, let's say on the 1, 2 boundary, must get labels which is either 1 or 2. And the ones inside, let's say there are 3 vertices inside, can just get anything arbitrary. I really don't care what they get. So let's say they get 2, 2, 3. Yeah. Okay. So these are the ingredients of Sperner's lemma, and so the lemma says something very powerful. So the Sperner's lemma then says, it says that every triangulated T with Sperner labeling, which I have just described to you, must have a elementary triangle. This I'll just denote as a triangle, elementary triangle with all 3 labels. By all 3 labels, currently I mean there must exist an elementary or baby triangle inside this whole big triangle, which is all 3 labels, 1, 2 and 3. So can someone spot a triangle, such a triangle for me? Like, do you see such a triangle? Yeah, you see, but I think you can't really pinpoint correctly, but yeah, I see you see one. So okay, there is one here, right? Yeah, so this is a elementary triangle which indeed has all labels 1, 2 and 3, right? So this is a very powerful lemma which just says that given this particular condition, a triangulated triangle T with Sperner labeling will always end up having a fully colored elementary triangle. Okay, so let me write this as well. Okay. So Technically, we say fully labeled or fully colored elementary triangle. Which just means that an elementary triangle with all labels. Elementary triangles where vertices, so if you collect the labels of its vertices, it should be the whole set 1, 2, 3 with all labels. Currently it is 1, 2 and 3. Yeah, I should also copy. Yep. Okay. So any problem, any questions, any doubt in the setting till now? It's all clear? Okay. Yeah. Say it again, 1, 2, 3, 9. No, which particular, are you talking about the boundary vertex? So which, so this particular 1, 2 edge? No. Yeah, yeah, 1, 2, 3, 3 is there. Yeah, yeah. Oh, no, no, no. Okay, so let me repeat. So the condition is about the boundary edge 1, 2. This is the 1, 2. Oh. So this is 1, 2 edge. This is 1, 3 edge, and this is 2, 3 edge. So Sperner labeling confines or has a constraint regarding the vertices on just these boundary edges. Inside I can just do any arbitrary labeling, I don't really care. You do anything inside, I'll still end up giving you a fully labeled elementary triangle. Okay? Yeah. Yeah. So again, just to repeat the statement, because I want you to all remember the statement for coming days or for coming months. So it says that Sperner's lemma states that whenever you have a triangle which is subdivided into elementary triangles and also also comes with a Sperner labeling such that these two properties are met. The first is all three main vertices get distinct labels, and the boundary vertices, let's say 1, 2 edge, all the vertices on this 1, 2 edge must get a label which is either 1 or 2. It is restricted to, or it is forbidden to get the label 3 for this particular edge which is 1, 2 edge. Okay, yeah. So again, for people looking for formal terms, this is called simplex in higher dimension, which is like n dimensions, and also this particular triangulation is again called triangulation only, that is the formal word. But so for this particular lecture, I'll just stick to triangles, but formally it's known as a simplex. If I have time, I'll again circle back to properly explain what a simplex is and how does it work for higher dimensions. But the arguments just go on for higher dimension easily. There is no new argument coming in the picture. Okay. Yeah. So all clear now? Yeah. Okay. So let me start with a proof. And also I do want to do the proof because it's, I don't know, it's super elegant and I do want to do it. So the proof, okay, so the proof comes with, let's say, a story. Let me assume that the whole big triangle is a house. Okay, the whole big triangle is a house. I don't know who resides in such a house, but it's a house. And all these elementary triangles, elementary or baby triangles, they are, let's say, rooms. So there are several rooms in the big house T, and I'll also define something known as a door. So this definition is quite important, and do focus here. So a door is something which, okay, so a door particularly here is an edge which has label 1, 2. Which has label 1, 2. So I will point out the doors here. So, yep. Okay, so there's one door I can see here. This is 1, 2. It's a door. There's another one sitting here, which is a door again. There's another one which is 1, 2. Okay, can someone tell me that on this particular edge, can I ever find a door? Why? Louder. Exactly. So I will really not find any door here. Again, the same argument goes here. I will definitely not find any door. I will specifically define a door as an edge having label 1 and 2. So I will not find a door here. I will not find a door here. But yeah, there may be doors inside. There's one here. There is one here. There is one here. There is one more. Okay, there are several doors. Okay. Am I missing any door now? Okay. Oh yeah, got it. Got it, yeah. So now, am I missing any door? So these squiggly lines represents doors here, okay? So it will be soon be clear that why am I saying them as a door. I'll basically walk through them. So therefore, it's a door. Okay, so before starting the argument, there are two observations which I would like to point out. The first one is about the number of doors. Again, I am confining myself to a lower dimension case, here a triangle, and all arguments do generalize. Okay. So number of doors on the boundary edge 1, 2. Boundary edge 1, 2. Okay. This is currently my notation for an edge. Yeah. Okay. So can someone tell me what would be the number, or can someone tell me the parity? Will it be odd? Will it be even? Will there even exist one? Yeah, odd is the correct answer, but why? It is correct. All twos. Oh, okay, yeah, all twos. Yeah. Yes, there. But yeah, the answer is correct, but formally, how do we say it?
It's like in a river crossing. You go from one place to reach two. Every time you reach like you connect from one to reach two.
Yes.
How many exchanges are making? 1 to 2, 2 to 1, 1 to 2, 2 to 1 like that. If you go from 2 to 2, there is no door.
Yes.
1 to 1 no door. So
yes.
you are making the change. That is all.
Okay.
Just like you are crossing the south of the river twice, so they will compensate.
No, but why odd? I get there would be one. Okay, so what is happening is I'm going from 1 to 2, and there's bunch of vertices here. I need to label them, and so somewhere along the line I must switch, right? Let's say I switch it here only, but let's say even after that, I don't know, I switch it once more. So let's say I switch it, but then to compensate this particular last switch, I have to have some 2 down the road, right? It can be the very last as well, but I need to have it, right? So after the first switch, the further switchings must be paired up to compensate one another, right? Because from now on, you can again consider this as a sub-instance of 1, 2, and therefore there again exist 1, right? The argument is clear, right? There must exist odd number of doors, which is these 1, 2 edges. On the boundary edge, the whole big 1, 2, right? Any doubt in here? This will be crucially used in the proof, so if there are any doubts, do ask me. Okay. So the first observation was about the doors, in particularly the parity or the number of doors you have on the boundary edge. Whenever I say boundary edge, it's the outermost boundary, the big 1, 2 edge, which is odd here. Okay, so the second observation would be about rooms and what kind of doors a room have, or what number of doors a room can have. Okay, I did not want to go to another page, but okay. I can, but yeah, let's see. Yeah. Okay, so the second observation is of the rooms, okay? So let me ask you this question. Can there exist a room with no door at all? Can there exist? No? Oh, okay. Just see the picture. Is there any room you can find which has no door? Yeah, okay. So there can be some rooms. So a room, remember a room I am saying is an elementary triangle. Okay, a room can have 0 doors. Can it have, I don't know, 2 doors? It's possible, right? It's something like this. So 0 door is something like this, and 1 door would be, I don't know, some label is repeating. In this case 1, in this case 2. So you have 1 door here, you have 1 door here. So you do end up with, you can end up with 2 doors. You can have 0 doors, you can have 2 doors. Can you have 3 doors? Yeah, okay. You cannot really have 0 doors. Okay, so what would be my next question? Okay, I shouldn't ask you to guess my next question, but okay. Can there be a room with exactly 1 door? Yes? What is, yeah? Yeah, exactly. So a room with 1 door, exactly 1 door, has this property that it has to be fully labeled. And that is the object we are looking for, or that is the object we are after. Okay, so a room can have 0, 1 or 2 doors. Okay, and the one having 1 door is our prime object. Okay. So you have 2 observations, and we'll use them while in the proof. So the second observation, just to repeat once more, it says that a room, by which I mean an elementary triangle, can have 0 door, 1 door, in which case it has to be a fully labeled elementary triangle, and it can have 2 doors. Fine, a label either 1 or either 2 repeats. Fine. Any doubt? Any doubts? It's clear? Clear at the back as well? Yeah. Okay. Okay, so now that I know that what I really want, I want a room with exactly 1 door. At least now I know at least I know some property of it. Yeah. Okay, so I'll start with the proof. And just give me 1 minute. Okay, so I'll start with the proof having those 2 observations in mind. But okay, so the proof is via walk, and it's also called proof via walk. I don't know. Okay, It's called path argument because you follow a path, a certain kind of path, or proof by walk. This is a very informal saying, and I think it's informal. Okay. Oh, also before that, I should also tell you that okay, this existence result was introduced by Simons, but I think he never published it, and it was published by Su in '99. So this reference will be up again on the course, the school website, and you can take a look in detail. It's a very fantastic paper, and you should all read the paper. It's a fun paper, yeah, he calls it as a trapdoor argument. Trapdoor argument. I don't know why, but maybe he traps the fully labeled triangle via his argument, and therefore he's calling it so. But okay. So what is my path? The first thing I do is remember this whole thing T was my house, and I can just enter the house via a door, and the door is, let's say, one door I can find here is this one, right? Let me use another color. Yeah. So let's say I enter the house via this door with having one on my left and two on my right. So I enter the house, good, no problem. And so what can happen? Either this particular room I have entered, this 1, 2, either this particular third vertex will be labeled 3, in which case I am done, right? I literally found the fully colored elementary triangle I was after. Otherwise, what will happen? It will be either 2 or 1. In which case, what is happening? Exactly, there's a second door for sure, because I already know there's a single door. So the 0 door room is not this one. It already has one door. It does not have exactly one because the third label is not 3, I checked, and therefore it has 2 doors. So let's say this is 2. So I'll basically have another door to exit the room and therefore enter another room. So via doors, I enter the room. If the particular room is fully labeled, I stop. I've reached my fully labeled room. Otherwise, I'll always have a second door to exit and continue this particular path. Okay? Do follow the path closely. Yeah. Okay. Yeah. So you always start your argument from the boundary edge. Oh, also, I do know that there exists one because I've just shown that they're odd. In particular, there does exist one. Okay. So I entered it. Okay, in this particular room I did not found the third label, but in place of it I found another door. So I exit the room. Again the same thing happened. The room was not fully labeled. I continue this particular path. I enter here. Again the same thing happened. No worries. Keep continuing. Again and again. But somehow I'm thrown out of the house. I wanted to end up at a fully labeled elementary triangle, but I don't know, I was not lucky and I was thrown out of the house. Now what do I do? Where's the another door? Yeah, you can see it here, but the formal argument is there are odd number of rooms, right? Odd number of doors. So these 2 doors, this one and this one are paired up, fine, no problem. I will enter. I know that there will always exist one door for me to re-enter the house. The house cannot just throw me outside just like that. It will give me another way to re-enter. Fine, good. Okay. So I enter here. Fine. I note that I again have one on my left and 2 on my right. And Again, this particular triangle did not have all three labels. I exit, no problem. Again, the same thing happened. But now finally, do you see where have I reached? I have reached my goal, my destination, which was a fully colored elementary triangle. I have reached the fully colored elementary triangle, but yeah, we will formally argue that this will always happen. Yeah. Just stare at the picture once for a minute or so, and see if the path is being understood properly. If there's any doubt in the path I'm following, do ask me. Okay. It's clear, the path. Do you want some more time to think and just stare at the picture, or should I move on? Okay, you guys are writing. Okay. So in essence, what we're doing is, I've got this Sperner labeled triangulation, and this triangulation of this particular big triangle. I have shown that I always have, at least to begin with, I always have a door to enter the house. I follow the path, and either I'll be thrown out of the house, which is okay. I'll always find another door to re-enter and finally end up at a fully labeled elementary triangle. Yeah. So the proof is almost complete. There's just one particular thing which we need to check. What is it? Is there anything left to be shown, or is it formally complete? Yeah. So I just need to show that these paths do not cycle back. Yeah. So can they ever cycle back? Why? They can't exist three doors. Yeah. Okay. So I'll I'll give a short proof for this, and a formal proof can be, I think, covered in tutorials. But the idea is every room has at most one entry door and has at most one exit door. So let's say for contradiction, you somehow re-enter some particular room. So you have to re-enter from particular door, which means, and let's say this is the first room you re-enter, and you re-enter from that dedicated entry door, which means that you would have entered the previous adjoining room as well, which is contradiction to the fact that this was the first room you re-entered. Yeah, but this has some other proof also, but yeah, this is a high level idea, and I think I think people do believe that you would not cycle back. A formal proof can be seen in tutorials, I believe. Yeah. Okay, good. The paths do not cycle back, and therefore I am bound. Okay, so there might be some paths which basically led me out of the house, but there will always exist a door which will end up eventually at a fully labeled elementary triangle. Okay? Fine. Now, also, just one more observation. Oh, okay. So before that, Sperner's lemma. So it says something stronger. It says that there exists a fully labeled elementary triangle, but it also says that there exists odd number of fully labeled elementary triangles. There always exists odd number of. So there's a heavy parity argument going on in the whole of Sperner's setup. So there exists odd number of fully labeled elementary triangles. Yeah. So we have shown the existence of one, but the existence of odd again comes from the fact that again I'm leaving this particular thing for tutorial, but again a very high level idea is what I'll give here. Okay. Let's say something like this is happening. This is 1, this is 2, this is 3. So right now what I'm proving is I'm giving a high level idea of the argument why there will always be an odd number of fully labeled elementary triangles. So let's say this is 1, this is 1, this is again 1. Okay, so just look at this particular thing. Yeah. Okay, just stare at this particular thing. Okay, so first of all, there does exist this elementary triangle, and again there does exist this elementary triangle. You can all see there are two triangles in this in this region which is bounded by green colored edges, okay? Just look at this particular subset of the whole triangle T, and I know that there exist two fully labeled elementary triangles here, but can someone tell me if any path, let's say this is 1, any path, and there are odd here, that's fine, but can someone tell me the reason why this particular argument, this particular path following argument will not let me reach these two fully labeled elementary triangles? Can you see an argument where whatever I do, starting with the door, 1, 2 door, I will never be able to reach these two elementary triangles. I'll reach something, I don't know where, it would be somewhere in the rest of the triangle, but I would definitely not be able to reach these two triangles. Can someone do remember the conditions of Sperner labeling here, but is it possible? So this is the only label I require. Anything else can be. I don't really care about the labels of remaining vertices. I don't know. Let's say. Yes, via 1, 2 door. It can never be crossed. Yes.
I cannot come down to this direction.
Yes.
Because to come down, I have to come either from left or from right. Left I cannot, I have this one.
Yes. Okay.
Only right hand side can be there. For right hand side also the top need to be there. That is also not available.
Okay.
So that's why I cannot go to this problem.
Yeah, somewhat true, but the argument is this particular bounded region has no 1, 2 door for me to even enter. Forget about reaching these triangles, I can't even enter this particular bounded region. So this is 1, 1, this is 1, 1, I can't enter. I can only enter from a 1, 2 door, remember? So even if, let's say, this is 1, 2, let's say. Oh, sorry. My bad. This should be 3. Yeah, I'm sorry. Okay, so I can't really enter from here because it's 1, 3. So just stare and convince yourself that you can't really enter this particular bounded region from a 1-2 door following this particular path following argument which I've just described. So there's no 1-2 door to even let me enter the whole bounded region. Okay. So what happens in such instances is this. So let me just start from here only. 1, 2, and there's a door, it's a door, right? Let me just start for the sake of argument. And I exit and I enter this particular room, I exit and I finally reach a 1, 2, 3 fully labeled elementary triangle. And again I do the same procedure, I start from here and do reach. So in effect, which can be formalized again in tutorials, the high level idea is there are always, if a particular fully labeled elementary triangle cannot be reached by the path following argument, they are always paired up. They can be reached from one another. And so since they come in pairs and the rest of them are odd, the total number of fully labeled elementary triangles is again odd. Because remember, here also you have odd number of doors. So every one door leads to one particular fully labeled elementary triangle, and so they are odd in number. At most you can have odd numbers from those doors, and the remaining ones are all paired up. So in particular it's like odd plus even, which we know is odd. So odd coming from those doors and following the path, and these are all paired up. So in total there will be odd number of fully labeled elementary triangles. Okay. Again, I know that I've given a high level idea which can be formalized. Okay, but for again the sake of time, I'll skip this. Okay, so this is Sperner's lemma. Is the proof clear? The proof was simple, right? And also good. So Sperner's lemma says that, let me get, yeah. So Sperner's lemma says that given this setup, the whole big triangle T subdivided into elementary triangles will again also having labels which follow this particular Sperner labeling, which is basically consistent with these two properties. You will always end up having odd number, or in particular will always exist one fully labeled elementary triangle. So again note that in this particular example also you would be able to have odd number. Is there any one? Okay. Oh, in this particular example there is no other elementary triangle, fully labeled elementary triangle. So it is one in particular which is odd. Yeah. So is it clear? Any doubts? Okay. So now you would be wondering what is the relation of whole of this Sperner's lemma to our cake cutting problem, right? How does envy freeness really come into picture, and how does it prove existence to begin with? Yeah. So again, I would like to emphasize on the fact that this is a very strong combinatorial result, and it has many applications. There are many variants of this particular. This is like a discrete variant. There's a topological or continuous variant which is called Brouwer's fixed-point theorem. There's another set cover equivalent which is called KKM lemma. If time permits, we'll see some of those in the coming days. But this and their variants have a lot of applications, not just in fair division, but in many other areas as well. So it's good to know this particularly cool lemma. And I don't know why is it called lemma. It should be, I don't know, maybe it sounds better with the word lemma. Okay, so let me now go to our cake division setup. Okay, so I'll do cake. Oh, okay. So I'll do cake cutting using Sperner's lemma. So in effect, Sperner's lemma, and you should, just to think ahead, that particular fully labeled elementary triangle in some way transforms to an envy-free cake cut. Yeah. Okay. So remember, for NV freeness again, I need, so okay, again these all can be generalized to higher dimensions where it's called simplices, and we can see them if we get time. But again here, let me, for the ease of presentation, have n equal to 3, which just means that there are 3, let's say there are 3 agents. This is a set of agents, okay? There are 3 agents and who have somehow gotten a cake and they want to divide it in an NV-free manner. Can they really do with continuous pieces? So the answer, as told, is indeed yes. So the first proof of existence came via Stromquist, who was the one who gave that strong negative result. But this is, let's say, the second proof, which comes via Sperner's lemma. Okay. So what I need is, okay. So this is my cake, which is being denoted or modeled as 0, 1 segment, and I want particular cuts, let's say 2 cuts, because I do want a continuous interval to be allocated to every of the 3 agents. I want, so therefore there will be n minus 1 cuts, which is in this particular case just 2 cuts. So let's say this is x1, this is x2, and this is x3. And I mean that x1 is the physical length of the piece from 0 to the first cut, x2 is the physical length of the piece from second cut to the third cut, and so is x3. So can someone tell me what does x1 plus x2 plus x3 is? This is equal to 1, right? And then we also have all these xi's are greater than or equal to 0. Yeah. Okay. So, okay, am I audible? Did something happen? Okay, so the idea is I'll plot some vertices and we'll see what happens. Let's say this is x1 axis, this is x2 axis, and this is x3 axis. So let's say this particular point is 1, 0, 0. So what does 1, 0, 0 represents? It represents that it's basically the whole x1 is equal to 1 and x2 and x3 are 0. So they are empty pieces. Okay, so these are like extreme cuts you can possibly have. Just give the whole cake to one particular agent and rest of the 2 goes empty-handed. Okay, so this is 0, 1, 0 and this is 0, 0, 1. Okay, so all these 3 points do represent a valid cake cut, right? Yeah, okay. But also now focus on this particular plane. Okay, so this particular plane, okay. So can someone tell me what is this plane? Can someone tell me the equation or anything about this plane? Yeah, this is exactly this particular set of points, right? Xi's are greater than or equal to 0 because I'm looking at the positive authent. And also they all sum up to 1. So it's that plane or hyperplane. Okay. So in particular, every cut on the cake can be represented by some point here. Okay. So let's say this is x, which is, let's say, x1, x2, x3. So this particular point does represent a valid cake cut, right? Yeah, okay. And so these are 3 extremes, and in between are the ones which are somewhere in between, right? But you all agree that every possible cake cut can be represented by some point lying on this plane, right? This is convincing to you, right? Okay. Okay, so if you think about it, this particular plane lies in 3 dimensions. I agree, but if you just look at the structure, it is indeed a 2D 2D triangle. Also plane, yeah. It's a chopped off plane, yeah, definitely. But it's a triangle. Okay. And if it's triangle, obviously Spooner's, okay. Anyway, the hope is to invoke Spooner's lemma at some point. But yeah, there's a triangle. Okay, so I'll just say that this is 1, 0, 0. This is 0, 1, 0, and this is 0, 0, 1. This is, let's say, my triangle T, which I considered in my Spooner's lemma. And yeah, this is the space in between. Okay, so the idea is to invoke a Spooner's lemma. For it to happen, I need a triangulation, and also primarily I need a Spooner labeling. That is the important part. I can triangulate it, fine. No one is stopping me. I can triangulate it right now. No one is really telling me anything. Okay. But the second thing I need is to have some sort of Spooner labeling on this particular triangulated triangle T. That is the most important thing, and it's not very difficult to do. Let's see. Okay, so to begin with, I'll say some assumptions on the preferences or the valuations. Valuation functions of these 3 agents ABC. Okay, so the first one is, okay, I'm just assuming that, let's say, given any cut, which is represented by x1, x2, x3, and remember these x1, x2, x3 are physical lengths of the pieces which is there in the division. So given any cut which indicates length, every agent must be able to, point, okay, this is my favorite piece. So he is given some cut and he should be able to tell me which is the piece which he likes the most. And note that if he really gets that particular piece, he would be envy free, irrespective of what other 2 agents get, because that is the particular piece he likes the most. Every agent must be able to tell their most preferred piece. Preferred piece, let's say this is, for some agent, this is this particular. So you should point and say that, okay, the piece first is the one which I prefer the most. And second assumption is like the hungry condition. So it just says that, okay, they are hungry, and if they get any non-empty piece of a cake, they are happy. They prefer it over getting nothing, because, yeah, let's say they are all just very hungry. So they all prefer a non-empty piece over an empty one. There's one more condition, or there's one more assumption on the valuation function, but I'll tell you when we come to that particular part. It would be helpful to tell later. Okay, just 2 very simple assumptions I've made. They are hungry in particular, and they can just given any cut, they can pinpoint, okay, this is the most preferred piece for me. Okay.